Okay, while everyone's filing in, maybe I'll just ask if there are any questions that anyone had so far. Yes?
What's going to be your favorite aspect
of today's lecture? Proving various C-theorems. That will be fun. Any other questions? The question was, what will be my favorite aspect of today's lecture? If you didn't hear that.
What is the difference between entropy and defect operator?
Entropy and defect operators. I'm not sure what the question.
Well, many properties of the entropy are similar to properties of inserting a defect operator on the boundary surface. So this is the leading order in the Rindler formula.
In the Rindler formula?
Yeah. So the formula for Rindler is the same as the one you would have if you had a defect operator inserted on the boundary surface. And in ADS-CFT, if that defect operator is due at the membrane.
Oh, I see the question. Okay. Yeah. So at least in ADS-CFT, I guess it's sort of a little bit less clear to see this from the boundary. But if you try to calculate these things, like twist operator correlation functions in ADS-CFT, then they're actually very different between when you're calculating the entanglement entropy and the Renyi entropy. So you remember there's this parameter n that we can freely change, and the entanglement entropy is the limit n goes to 1. And one important property of these twist operators is that their dimensions, or if you like, their tension in ADS is proportional to n minus 1. So if n is, in fact, they're proportional to c times n minus 1, which is 1 over g Newton times n minus 1. So they, if you treat them where n is not close to 1, then they have a very big back reaction on the bulk spacetime. And if you try to write down a simple formula for the Renyi entropies, for example, it's very difficult because the spacetime gets changed. So your probe changes the spacetime. Is that what you were asking, I guess?
Well, I guess Renyi entropies are a result of inserting a defect operator. But when you take the limit of n going to 1, it's not the same as inserting an operator. And that's related to the fact that it's trace of rho log rho and it's a nonlinear function of rho.
Yeah, certainly. So that's another point. I mean, these are operators. The twist operators that we're talking, I tried to make this point. I mean, these operators we're talking about, the twist operators are really only, genuine operators and defect operators when n is an integer. So you have to do something funny. You analytically continue them and send n to 1. And in particular, as n goes to 1, you get trace rho log rho. Trace rho log rho is in some sense a state-dependent observable, right? It's not the expectation value of some operator. It's the expectation value of the log of the density matrix. So that depends on the state. Okay. Are there any other questions? Yes?
Could you repeat how we actually find the partition function of the n-sheet cover?
It's sort of case by case. So some things are more difficult than some cases are more difficult than others. So the case that I'm going to that I talked about at the end, well, it's related to a case where you're just calculating the operator dimensions of the twist operators. Then you can explicitly calculate the partition function just using conformal mapping techniques. However, for other situations, it's more complicated. So,
the interval gas study?
Yeah.
You'll be able to map it, you'll be able to use the conformal mapping.
Yeah, you can solve that one. Yeah. Any other questions? Yes.
I was just wondering, in cases not that you weren't there, that people weren't able to calculate like the general n, but they calculated
Yes. Oh, when can you do that? Is the question when?
Or, well, like what cases have been done?
Yeah, so I think I can say a few things about it. So the question is, in which cases have people successfully computed the Renyi entropies and analytically continued them? Free fermions is an example. So I should say, yeah, so it depends on what you're calculating. So in a CFT, for a single interval, you can just do the calculation for any CFT. But for more than a single interval, then it's very hard. So it's been done for free fermions. You can do it in some kind of asymptotic expansion, and I'll mention that. And it's been done for ADS CFT. So, yeah.
You can do the Rennies without the analytic continuation for many more theories. Was that the question?
The Rennies. The question was whether you can get the analytic continuation, I think. Yeah. Mm-hmm. Yeah, but you can just study the Renyi entropies, the second Renyi entropies numerically. You can do all sorts of things. But actually, trying to extrapolate to get the entanglement entropy is a very difficult problem then. So you really need, I think it's important to emphasize, you really need some kind of analytic, you need some analytic handle on it. Yeah. Yes?
Are the entanglement inequalities like secretly hidden in the axioms of like QFT or?
I think that's an open question. Yeah, I don't know. Yeah.
What was the question?
Whether the entanglement inequalities are secretly hidden in the definition of quantum field theory. So, yeah. Okay, so let me continue. Unless, are there more questions? Yes?
What there are situations where Renyi attributes are not as good as the entanglement are there
there are actually many situations like that. Entanglement entropy satisfies sort of additional inequalities than Renyi entropies. So it has sort of more nice properties. And so there are situations where the Renyi entropies and the entanglement entropies give a very different picture of what's going on. So yeah. Characterizing phase transitions. So the question was whether the Renyi entropies or the entanglement entropies are better at characterizing phase transitions. Yeah, I think they're probably both good at doing that, I would guess. Yeah. Yes?
Does knowing it for all integer n specify unique analytic continuation for all n?
With the additional assumption which goes into Carlson's theorem, which is an assumption about the growth at infinity.
So related to the question.
Yeah.
So we know that different n for Renyi entropy can distinguish different order of the chaos, or say, right? Then the different order of the phase transition, has anything related to that?
I'm not sure what you mean by different orders of chaos.
Can measure the extent of the chaos of some example. Say if it's a harm example, then you have to use the n to check, right? So if it's like pure design, then you only need
Yeah, okay. This is not my expertise, so I'm not going to be able to give a good answer to that. I think there are other people in the audience that could probably answer that better than me. But yeah, so I'll deflect that question. Yes? Sorry. I will not mention that. But I can talk about it. But probably later, so let me defer that one. Okay. All right. Let's move. Let's get going. So from last time we were talking about orbifold theories. So we imagine we had n copies of our CFT, and then on this n copy we had some symmetry G, which cyclically permutes, cyclic permutation. And then when we consider the orbifold theory, we mod out by this Zn symmetry, then we get new objects, which were these twist operators. So if we look at some sort of regular point on our Euclidean manifold, and we sort of imagine going around this point, we had sort of n copies of the theory, and they don't talk to each other. However, if you're circling around one of these twist operators, then as you go around, the definition of the twist operator is that as you go around, you cycle between the different replicas. So that means you get a bigger circle. It goes around n times. And based on this, you could use the Casimir energy of the CFT when you map it to the cylinder to figure out the dimension of these operators. And that's what we ended last time with. So the dimension of these twist operators, so this is some local operator, which has dimension, which is C over 12 n minus 1 over n. So now we can go back and look at what we were trying to calculate, right? So we were trying to calculate before the partition function on some manifold which looked like, so Mn looked like this with two twist operator insertions. So, and there's always n copies here. It's not hard to guess that this is computed now by a two-point function of these twist operators. Okay, so there's some location, Z1, Z2, and this is some two-point function. But one thing I didn't say, and you can convince yourself of, is that these operators are primary, which means that this two-point function is fixed by conformal invariance. So in fact, it's just and this number, some constant, Z1 minus Z2 to the 2 delta sigma. And so maybe I should call this something else. Let me call it kappa. So that the claim is that Z of Mn is at least proportional to this two-point function. But for our purposes, we also kind of want to fix this normalization. And to actually fix this normalization, let's just make these equal. Then we sort of really have to confront computing the partition function of this manifold. This has at least given us the dependence on Z1 and Z2. But what this constant is sort of secretly hiding is the fact that there's some singularity on this manifold. And you have to, at some point, you have to regulate that. Okay? And that singularity is the same thing that we've talked about for entanglement entropy. It's related to these UV divergences here. Okay. So if you do that more carefully, then you can convince yourself. So I'll describe a little bit later how you might go about doing that. But you regulate the manifold with some parameter epsilon, where the parameter epsilon is some short distance scale close to the twist operator. Some epsilon. And then if you divide out by the normalization that we needed to divide out by in the Renyi entropies, then you just find Z1 minus Z2 over this cutoff to the power minus 2 delta sigma. And okay, so we put one of our, yeah.
Why is there divergence here?
Well, if we interpret it as the partition function on this manifold is singular. So
Because of but you're saying that even on M1 there's singularity. So
yeah, I probably shouldn't have done that. You're right. This is also an infrared divergence. You have to deal with that to make sense of this. So yeah.
I have a comment. So
yeah.
you mentioned that if you divide by Zn, then this is a local operator.
Yes.
But I feel it's better not to divide by Zn and remember that there is a cat.
Yeah.
Really think of them as defect operators with a topological codimension one.
I would like to disagree a little bit. I think it's useful to think of them as local twist operators, but you have to worry about global issues. So
Well, the point is that if you had a compact circle, then it matters in which direction the cat is.
exactly, yeah. So there are times when it's important to do that, but there are other times when it's convenient to have it really as a local operator. So there's other ways to deal with the global issues. But yeah. At least for this calculation, it's nice to think of this as a twist operator and a local twist operator and compute its dimension that way.
I mean, maybe the way to say it is that the Z of Mn is really the fundamental thing.
Yeah,
and
that's right.
The twist operator is a trick for computing it.
That's right, yeah. So if you ever get confused about twist operators and whether they're local or not, you should just go back to the left-hand side.
Because you could say you have this topological line operator with two things at the end, and then conformal symmetry just ensures you have these dimensions.
Yeah, okay. But then when you want to compute higher order things, then it's nice to have a description in terms of a local operator.
My feeling is that you should never need it because it's really not there in the line definition.
I think it's useful for calculations, and I can tell you maybe offline an example where it's important. Yeah. Okay, so now we come to the hardest part in the lecture. So firstly, let me put Z1 to be 0, Z2 to be R. And so remember what we're calculating is we're trying to calculate the Renyi entropies of the reduced density matrix for this interval. And this thing, remember, was calculating for us trace row A, so this is now A, trace row A to the n. And then just using this expression and taking logs. So remember, we have to also take a log of this and multiply by this factor. And then when you do that, you find Sn is 2 delta sigma over n minus 1 log r over epsilon, which then which is equal to C. Okay, so the hardest part in the lecture now is, well, this is trace row to the n. This is the way I've described it is in terms of this overfold theory at integer n. And so we've only found the Renyi entropies at integer n, and now we have to find an analytic continuation. So can anyone guess what the analytic continuation of this is? In particular, we only need the analytic continuation in this region, so you can not worry about the pole there. Right, it's just this, okay? So that's the analytic continuation, and so that's actually not very hard. Okay, so then we take that and we compute the von Neumann entropy by taking a limit n to 1, and that's also easy to take here. And I'm missing a factor, C over 6. And then you take n to 1, and you get the formula that you've seen many times now. Now, given this setup, at least in terms of this correlation function in the overfold theory, then we can actually just calculate many other cases. In particular, we can use the fact that the twist operator transforms like a primary operator, so under conformal transformations. So something like this, sigma twist operator And now we can do various conformal mappings to take this picture into various other situations, which the answer of which Matt Hedrick has written down for us. So I'm going to leave this as an exercise, but as an exercise, I'll draw pictures for you, and then I want you to take those pictures and turn them into the Renyi entropies in each of these situations. So we want to apply a map from some, say, space Z, which is what we had here, sigma n, sigma minus n. I will put a branch cut there. And then you're going to use the exponential map. So, so you're going to use the fact that Z is exponential of W based at some point. So the point is the origin of this map, and that's what I'm drawing here. And then when you do that, you get circles here, and this maps to a cylinder. And these are the circles on the cylinder. And going radially out, as usual, just moves in the time direction here. But now we have these twist operators. But now we have these twist operators inserted somewhere here on some fixed radius, like this. Okay. So what is this? What is this calculating for us? Well, we can now just sort of backtrack and see what this is doing. Well, it's computing the path integral on the infinite cylinder. So this is infinite minus infinity to infinity up to the t is 0 slice, where it computes some state, which is the vacuum state on the cylinder. And then the twist operators are taking for you the partial trace. And in n copies, you're computing. So this is the Renyi. So you get trace rho a to the n, where now rho a is the trace of a complement, which is now this region here of the vacuum on the cylinder. Okay, and so that's a situation that. So that answer. Sorry, I should say. The answer for the entanglement entropy, Matt Hedrick wrote down in his lectures, and this gives you the Renyi entropies, okay? And the Renyi entropies are really simply related to the entanglement entropy just by this factor here. Because all of these conformal transformations sort of just give you these overall factors of the scaling dimension. When you take the log, it just becomes an overall factor. Yes?
I have a question.
Yeah.
So I was wondering what happens in the holographic dual corresponding to these twist operators. Is there a surface which is anchored on these 2 points or something?
You can think of it that way. Yeah, so there is a surface. So to calculate these things in ADS-CFT, you have to find, so actually these calculations are really simple in ADS-CFT. I'll describe harder ones later. But you have to find some, this is some Euclidean manifold, and so to compute the partition function, you need to find some solution to Einstein's equations, which has that as the boundary. And so what happens is that there is a natural surface that ends on these twist operators, which is a fixed point of, there's a Zn, you assume that there's a Zn symmetry in the bulk. Sorry?
Is it a codimension 2 surface?
It's a codimension 2 surface, yeah. So you assume that the bulk spacetime maintains the Zn symmetry of the boundary, which is an assumption. But if that's the case, then there can be fixed points of the Zn symmetry, and those fixed points are exactly live on this surface that you're interested in. And in the replica trick, and using Juan and Aitor's discussion of this, then that surface becomes the entanglement entropy, becomes the RT surface.
Is there any role of conical defects?
Yeah, I mean, it's playing a role. What's important, though, is that gravity is smoothing out the deficit angle. So gravity actually just smooths everything out. And so instead of having on the boundary, you have some kind of conical excess, and in the bulk you have something which is smooth, and the way to characterize that, the point is this fixed point of the CN symmetry, but it's a smooth point in the bulk for integer n.
And is there any way to see this from a brain perspective? Distinguishing of intermediate CFTs in compactly different brains.
Yeah, so this is a whole discussion that I wasn't planning to get into, but I can tell you offline. So the question is all about how to do this in ADS-CFT. No, I mean, there's no brains. It's just gravity. Yeah.
Sorry, what?
Yes?
Going back to 2-point functions of the which field, could you write the OPE structure as the 2-point functions of the which field, and what kind of operator do I use on the right hand side?
I will talk about that. Maybe, if I have time. Okay. Other questions? Okay, so let me very quickly go through the. So I should say this is kind of a trivial case actually, and actually don't need twist operators to compute this at all. And this business about the analytic continuation is a bit of a lie because you can actually just calculate it when n is not an integer. And the way you calculate it in all of these cases is that you can use, well, okay, so all of these cases can be mapped. Sorry, I forgot to do the next case. Well, okay, so you can, so this is homework 1. Sorry, I forgot to, there's another case that you can solve in 2-dimensional CFTs. We can compute the Renyi entropies, which is if I have twist operators like this, and then I do an exponential map based here. So this is the base of my cylinder, and now I'm going to draw the cylinder in the different direction. And so going around here is like going around these circles here. And so if you think what's happening, you go around these circles. As you move out along this direction, which is now a spatial direction, which is now thought of as a spatial direction, then eventually you'll hit the twist operators. And so they're inserted here. And so you think of this as the time direction, but it's periodic, which means that you're computing a thermal partition function. You're using the thermal density matrix, and then you're partial tracing the thermal density matrix. So this gives you the thermal Renyi entropies on the infinite plane. So this is the thermal Renyies, and again, Matt wrote this case down for the entanglement entropy, and you can use this exponential map and this formula to calculate. So that's another exercise. Okay, so yeah, so I was in the middle of saying, so this is kind of trivial. So all of these cases, again, can be mapped back to this interval, just undoing this transformation. And this interval, you can do a conformal transformation that leaves invariant the vacuum on the plane to take the twist operators, one to the origin, and the other one to infinity. Okay, and so now your region A goes from 0 to infinity, and so what would this compute? Well, this is Rindler space, right? So you can map everything back to Rindler space, and again, in Rindler space, we know what the modular Hamiltonian is, Ka. And so in all of these cases, we also know what the modular Hamiltonian is, just doing these conformal transformations. And you can compute Renyi entropies now by trace rho A to the alpha now, and just to make it clear that it doesn't have to be integer, as trace e to the minus alpha Ka, which is just a thermal partition function where you take the temperature to be different to the one that you did for the entanglement entropy. Okay, and this can be calculated independently in all of these cases, and so it's not actually true that we're doing any analytic continuation. So we know the answer. Okay. Okay, are there any questions about that? Yes? The correlation here, well, so the space dependence is sort of fixed by conformal invariance. Now, if you're not in a CFT, then yeah, it could. I don't know where Nancy. So you know, all of the n dependence sits in the dimensions of the operators. Okay. All right. So now let's do a more non-trivial case. Let me go up here. Which is, let's say you wanted to calculate the mutual information, okay? So the mutual information, part of the mutual information, you have to compute the entanglement entropy of two intervals. Okay, so A1 and A2. Question? So A1 and A2, so you draw the same pictures that we've been drawing like this, and we have n copies. So now we can, you know, we have two options when we do. So this calculates trace row A1, A2 to the n, where the A1 and A2 are these intervals, and then you're tracing over everything else. Okay. Okay. So now we have two options. One is there's always sort of two options. One is to think about this as a partition function on some manifold, which is defined by this picture. And this is a somewhat complicated manifold. So this is option one, or option two is we can use twist operators. So let me say a little bit about both of these options. So the first one, it's not totally clear that this is, well, how to think about this manifold, right? This is some complicated thing. It has singularities indeed. So if we just take the metric on, you know, this is flat space here, so the metric in holomorphic coordinates is dz bar. And then we imagine, you know, what's happening as we go close to one of these points here. So there's some conical excess singularity that lives close to one of these points. And what we can do is if we go close to that point, we can sort of unwrap the conical singularity. We can make a coordinate transformation. So this is a z1 here. To a new coordinate, which I'll call y. And I put a factor of n here. And so notice that as I go around z1, as I go around y one time in my coordinate y, I go e to the I 2 pi y, and I come back to myself. Then according to this equation, I cycle around z1 n times, okay? So in terms of the y coordinate, this should be at least, should look smooth, right? But then, so this point here, so it gets mapped to something smooth in the y-plane. However, you'll also have to look at the metric, and under this transformation, the metric goes like, well, you just plug in z in terms of y, and you find something like y bar n minus 1 dy dy bar. And so up to some factor that lives at the front here, the metric is flat in the y-plane, so it's dy dy bar here. And so, you know, remember I told you before, CFTs don't really care about these conformal factors because the trace of the stress tensor vanishes. That's almost true, except in even dimensions, there's an anomaly. So when you try to calculate things like the partition function on Mn, when you do this transformation and then remove this factor to make this a smooth space, you always get some anomalous term, which in this case is the Liouville action. So it's the Liouville action for this mode here. So if I write this as e to the 2 phi phi L. So I'm not going to describe what this action is, but you can look it up and you can work it out. But in particular, this factor is singular, and so this action is still singular. So you still have to regulate this action, and you do that by cutting things off at epsilon, and that's how you get all this cutoff dependence. Okay, but when you do that, you can actually do this globally, and it gives you a picture of this space, which is maybe it's a cartoon at least, which is just some Riemann surface with some number of handles. Okay, so that's all this is. So the partition function up to this factor is given by the partition function on this space. Yes?
When you compute the Renyi entropy, you move Zn over Z1 to the n, so does that Rindler action just cancel out?
It would if you did everything the same on each sheet. Well, at the end of the day, it does. However, this is actually not doing the same thing on each sheet. So yeah, it doesn't cancel. Mm-hmm. Yes?
This only implements this twist at one point. You have 4 points where you want to implement it.
Yeah, so you have to do this in a global way. That's actually a little complicated, but you can do it.
So here the point is I unfold one interval, say A1. Make the A1 interval in the Y plane to have no branch cut.
No, I'm just doing this locally. So this is a local thing. You have to do a more complicated global thing to see this picture. In fact, this is just a cartoon. Yeah. However, there's actually various theorems. I mean, this is some mathematical structure, and there's a way to calculate the genus of this surface just given these twist operators called the Riemann-Hurwitz relation. And so there's a whole math behind this. I'm just trying to give you a cartoon of this. So in particular, you can use that relation to find out the genus of this surface, and the genus is n minus 1. Okay, so it will at least make sense that when n is 1, the genus is 0. Yeah, but one thing to emphasize is that if n is not an integer, this makes no sense, right? Okay, so another thing to say is that this Riemann surface has various, you can describe it has various sort of shapes, and there's some parameter space of those shapes, which is just the complex structure moduli space, and this particular surface is just a very particular slice through the moduli space of these surfaces.
Sorry, so QFT is defined on this Riemann surface?
Yeah. Mm-hmm. So you want to compute partition functions, just one CFT. Yeah. So all the n copies, if you like, are now just here.
These twist operators are DTS twist operators also?
Nothing to do with supersymmetry, no.
But it's a curve, if it's a curve vector, then supersymmetry is going to be there's some curve metric like constant negative curvature.
I'm not sure what the question is. Sorry.
I'm asking if the CFT is defined on this curve surface.
Yes. Yeah. No operators, yeah. Mm-hmm. So yeah, maybe I'm not understanding.
There are no covalently constant spinors on a curved surface until unless you introduce some twist there. So I was wondering if this is the separate case.
I think Matt can answer that. He's written a paper on it. Yeah.
Sorry, what?
You have to worry about fermion boundary conditions. Let's leave it at that.
Yeah.
So transforming to the genus picture is can you apply to any set, not only the fermion?
Yeah. So this works for any theory, except yeah, you might have to worry about twisted sectors, and yeah.
And why justification is not like the 4-point function of the twist operators?
Well, the 4-point function of twist operators I claim can be mapped to this partition function.
Oh, okay.
Yeah.
So like ordinary techniques of studying conformal blocks of 4-point function, would that work? Or that
Yeah, so that's one way to sort of get a handle on this. Yeah, so you can map between the two, and you can try to understand this from that and that from this. Yeah. That's okay. So good. Okay, so the other option is to compute. So this was option 1, and option 2 is to use twist operators, and then you can write a fairly explicit expression for the mutual information, for the Renyi mutual information. So this is the same as the entanglement entropy mutual information, except you just change the von Neumann entropies to Renyi entropies. And it's complicated expression in terms of twist operators, sigma minus n z2, sigma n z3. And then because you're computing the mutual information, you also divide out by just the twist operators of each interval. And that just removes the entropies, the Renyi entropies. So I think actually I got the sign wrong, because the entanglement entropy the mutual information is SA1 plus SA2 minus SA1 A2. So that's the Renyi version of that. Yes.
Can you write a little bigger, please?
Maybe I could just, I'll just write it here. Sigma n, it's just products of twist operators at the locations of the twist fields, at the locations of the boundaries of the intervals. Okay, so it's that. Okay, good. And so it turns out that because this is a ratio of a 4-point function with these 2-point functions, you can, there's no, the only thing that this depends on is the cross ratios. So this is a conformally invariant function, and there's no other scales. In particular, all of the, as Matt said, all of the regulator, as long as you regulate everything in the same way, all of the divergences, the epsilon dependence vanishes. And so there's no other scales here, so this can only be a function of cross ratios. So the differences in these coordinates, C3. Okay, so it turns out, so let me say, so there's two ways to do these kinds of calculations, and they're useful for different things. So this way is useful for ADS-CFT. So in particular, what you can try to do is try to fill in this Riemann surface with some ADS-3 geometry. And yeah, so I've tried to find solutions that do that in the past, and they're rather complicated, but you can do it. And this is convenient for, this is convenient for formulating the mutual information as some conformal block expansion. And so let me very briefly describe that. So, what you think of is take the intervals to be very, separated by a long distance. So this is some L. And at long distances, so what I mean by long distance is, you know, let's hold these two R is fixed, so L is much, much bigger than R1, R2. Then what you can do is you can do in this picture, then you can you can do a conformal block expansion, but just to be very basic about this, all you do is you think of the twist operators as, well, you take the two twist operators, in some sense they're coming close to each other, and then you draw a circle around those two twist operators, and then you use the state operator correspondence that I referred to before to say that instead of thinking about this as two twist operator insertions, I can just think of this as some local operator insertion with some up to some coefficient. So some sum over local operators with these OPE coefficients. And then you can calculate these OPE coefficients, and a conformal block is where you just compute the contribution from some primary operator and all of its descendants here. So it's sort of interesting to ask, what is the leading correction that you get at very long distances? So I take L very large, what is the leading answer? So long distances. So the question becomes a question of which operators I should use here. Okay? So basically, why is that? Well, because once I do this replacement, and I do it for this twist operator and this twist operator, then I get the 4 twist operators in some approximation. Well, it looks like some sum over these coefficients. And then you just have 2-point functions here, separated by some long distance, L. And so these decay with L to the dimension of the operator. So it turns out the question which operator dominates, it actually depends. So it's different for the entanglement entropy compared to the von Neumann entropy. The Renyi entropies compared to the von Neumann entropies. So it's different for these two. So in particular, what happens is an important point is that the operators that you should pick here are really operators in this Oberfold theory, in this CFT times n, right? So this n CFT. And so the leading operators that you might guess just have some operator inserted in one of the CFTs, and then a unit operator inserted in all of the other CFTs, right? And then, because of the projection, you also have to sum over the cyclic permutations. And so this is some operator that you can use here. However, it turns out that you can calculate the OPE coefficients of this operator, and you find Ci sigma sigma goes like n minus 1. And here I should square that, so I get n minus, so this is as n goes to 1. So this goes like n minus 1 squared. To compute the entanglement entropy, remember, you always divide out by this factor of n minus 1. That cancels one of them, but this still vanishes in the limit. So these operators don't contribute in the entanglement entropy at long distances. And the leading operator, and this.
Why the 3-point coefficient
Yeah, actually, so it turns out that actually in 2D, how does this work again? These OPE coefficients vanish for all primary operators except the stress tensor, which is not a primary operator. So I mean Virasoro primary. And then you calculate these OPE coefficients essentially by doing a conformal transformation and unwrapping these twist operators. So for the stress tensor, it's the stress tensor 1-point function. But the stress tensor 1-point function is non-zero because there's always this trace anomaly. However, it vanishes when you go back to the plane. So it's proportional to n minus 1.
Can you also explain what's exactly happening holographically? I mean, the gravity theory?
Maybe I'll say a few words on that after I'm done, yeah. I mean, it's basically the same. So in the gravitational theory, this is the same. So I wrote a paper with Cesar, I don't know if Cesar Algon is maybe in the audience, where we showed that these were the same. Well, you're basically computing correlations between distant regions, and you're sort of understanding what is giving you those correlations. And in the bulk, there's some quantum fields, but the quantum fields also have these properties, and you just compute, and you find the same answer. Okay, so, but I wanted to get to the leading correction. So leading for the von Neumann entropy comes from operators that look like this, O1, and on the Kth sheet, you put the same operator. So this is some operator in the original CFT, and then you take a tensor product of operators, but now you put two operators. So you're kind of exchanging two operators in this operator product expansion. And then you can compute, well, it's a little bit harder to compute this, but you find it's non-zero. And so the mutual information decays as L to 4 times the dimension of this operator here. And the reason it's 4, usually, correlation functions decay as, L to the minus twice the dimension of the operator. But it's 4 because we have two of these operators. So the dimension of this operator is just twice the dimension of that operator. Okay, and actually, it turns out that this sort of had to be the case, because you can prove a bound on the mutual information, or a lower bound on the mutual information, given correlation functions. And so this is not the Renyi mutual information, this is the von Neumann mutual information. You can prove that the mutual information of I1, I2, and I will not go into this, is bounded by connected correlation functions of operators in the two different regions. So this is just the connected correlation function squared. But there's an issue here in that these operators need to be bounded operators. So this is the operator norm. So if they were unbounded, this would be infinite, and this would be a useless equation. However, if you use bounded operators, then you can prove this bound. Now, the operators that we're talking about here are unbounded, so it's sort of not totally easy how to connect these two. But you can sort of schematically think that, one way to make a bounded operator out of one of these local operators is first to smear it over the region. But this is still unbounded. So one way to make it bounded is to, if this is Hermitian, you just make it into a unitary operator. And then the norm of a unitary operator is just 1. Yes?
Maybe I might think that OP should also depend on the leading order, should also depend on the orientation of R1 and R2.
Say
It's not the case.
Say that again?
I mean, that correlation function.
Yes.
They should also depend on the orientation of these R1 and R2.
Of the twist operators?
Yeah.
The orientation is fixed. So it's fixed.
If it orient differently, then I will get a different. Is it true? It's a naive question.
You get phases, I think.
Crazy.
But maybe not.
I mean, I'm thinking.
Yeah, you get phases.
Dipole, so when you have dipole at large distances, and there's still a theta angle.
Yeah, I think so. I think so. Okay, so All right, so but the fact that this is squared is somehow consistent with the fact that you got, you know, the correlation function squared, right? So this factor of 4 means that you're actually computing correlation functions of this operator squared. And you know, the bound didn't apply to the Renyi entropies, but it applied where we don't find this behavior, but it does apply to the mutual information.
Does that inequality have a name?
This inequality is, well, it has various, it's derived with inequalities with names, which I can tell you. There's the Pinsker inequality, and you use the Holder inequality as well. So you can, yeah. But it's also in a paper by Verstrada, Wolf, and I forget the exact reference. Et al. And yeah. Yeah.
Nomination of 2 or that for like random contributions?
Yeah. So this was the one. This is n is 1.
How does it change for you?
Well, there are other operators that contribute, and it sort of depends. Yeah.
Here, the second line is multiplied with the first line?
No. This is just this is an example. Sorry, this is an example of how to make a bounded operator. And then you can try to put this in here, and you do find things that decay with some power, with the same power as this. So this is for any operators that you construct in the region A1 and A2, but they have to be bounded operators. So okay. You can try to do that, and there's some tricks, but yeah. Okay. All right, so let me move on to C-theorems. So, okay, so there's some questions. Say again? Which monodromy? Which ones do you want to wind around? Which ones? 3 around 2. 3 around 2. Yes, I'm sure there's some meaning to it. In terms of the Renyi entropies, I'm not really sure. It might have some meaning when you look at time-dependent quantities. Yeah. Yeah. Mm-hmm. Okay. All right. So let's move on to another topic, which is entropic C-theorems. Okay, you know, I sort of flashed these formulas before, so I'll remind you. So recall that you can, well, we've done one of these, but you can do the other ones in actually sort of similar ways. But at a CFT fixed point, for a ball-shaped region, so in various dimensions, the entanglement entropy has some universal term in it, which is, depends on the dimension, but in 2 dimensions it's this C over 3 R over epsilon. It's minus F in 3 dimensions, and minus 2A log R over epsilon in 4 dimensions. So here, you know, there's a, well, C over 3. So here there's a, you know, in both of these there's an area term that I've dropped because I'm talking about the universal term. Now, all of these quantities are interesting because they have some monotonicity behavior under RG flow. But they're also unified by the fact, well, they're unified here by the fact that they are all appearing as this universal term in the entanglement entropy. They also universally appear in the appropriate partition function on a D sphere in various dimensions. And this all just comes from, well, in D is 2 and 4, this follows from the trace anomaly, which I've alluded to, which is just the statement that in a CFT, the stress tensor is traceless, except if you put the CFT on a curved manifold, then you pick up corrections. So in 2 dimensions, you get this C over 6 times the 2-dimensional Euler density, and then A over 2 times the 4-dimensional Euler density in 4 dimensions. And then there's some corrections here that come from our Weil squared term.
Sorry, so this is in the UV?
Sorry?
These entanglement entropies are in the UV CFT?
Yeah, so I have it, this is at a CFT fixed point. So no flows. Just at any fixed point, it looks like this. Okay, so based on this, you can then compute the partition function on the D sphere in these 2 dimensions, and this term drops out because SD is conformally flat. And then you find that that in in these, at least in even dimensions, these terms C and A appear with some divergence, some log divergence in a very similar way to this. So that's at the fixed point. So now we're sort of going to try to ask what happens as we turn on some coupling. So we deform with some relevant operator. So we'll start at the UV fixed point, and then we'll So away from the fixed point, so what I'm imagining is, okay, you take the CFT and the UV, maybe I should call this I, the action, and then you deform it by some operator. Add some relevant operator with some, sorry?
That's not the genus of the unit. Something else.
No more, yeah, so we're back to sort of simple situations. We're going to think about spheres now, so there's no genus. Okay, so now, right, so what happens? Well, various things can happen. There's some cartoon of the RG flow that we can draw. So some cartoon. We start at some CFT1, and then we can flow. Maybe we can flow to some gapped theory, or we can flow to some other CFT, which then can flow to another CFT, right? And then this can flow to the gapped theory, and so you have some cartoon of sort of coupling space, and you're flowing in this space. But this sort of natural question, which is, we think about as you undergo RG flow, you're sort of, as you change your scale, you're removing degrees of freedom roughly because massive particles, if there are any massive particles, they decouple, and so the degrees of freedom is going down, so it sort of stands to reason that you can't, there's certain flows that you can't do, right? So you can't go back, for example, or you can't go in cycles like this. So you can't go back. This should not be allowed. And so how would you go about showing that? Well, if you can find a quantity that somehow measures too far, that somehow, I want that one, measures the degrees of freedom, and you can, by that you sort of mean almost by definition that under these flows, it should decrease, then you can prove that there's no cycles and funny things can't happen. So these are called C-theorems. So what we're looking for is some quantity that's sort of intrinsic to the fixed point. So this is some QFT1. So there's some quantity I'll call C1. There's some quantity C2, some quantity C3. And so C1, C2, C3 intrinsic to the fixed point. So it has some definition at the fixed point. And under renormalization group flow, CUV should be bigger than CIR. So this is a C-theorem. And there's various forms that you can demand, but this is the one that I'll think about. But it turns out that all these quantities that appear in the bowl-shaped region for entanglement entropy have some C-theorem. So in 2, 3, and 4 dimensions, there's C, A, and F, which satisfy this. And so, because they appear in the entanglement entropy, it's reasonable to guess that you can prove that they're that they satisfy this property using entanglement entropy techniques. And of course, this subject was really pioneered by Horacio Cassini, Marina Horta, and they have a lot of interesting papers on this, and I'm going to describe at least one.
So these are for ball-shaped regions, right?
Yeah. So yeah. So no, these quantities are believed to be, well, I mean, they're proven to be C functions, or C-theorems have been proven for these quantities, and they happen to appear in the entanglement entropy of a ball-shaped region. Okay.
I was wondering if you have flat regions, these C-theorems.
For flat regions? Yeah, no, I mean, you can try that. You can try other regions, but as soon as you, like, for example, if you look at a flat region and you found that it was determined by some other quantity that independently is not an RG monotone, you can just do some calculations and check it, then that's typically what happens. So I think it's for some reason it's the balls. It's the balls that work. They're the most symmetric, so maybe that's not so surprising, but okay, so how are we going to study this? Well, let's just take one of these RG flows, and we're going to describe it as follows. We're going to describe it as I sort of motivated here. So we take the CFT, we have some coupling, and we deform the theory by some relevant operator. There's some UV cutoff that I'm just going to hold fixed. And then so there's some UV cutoff, epsilon that I'll hold fixed. And we're going to think about this flow that we get, so the theory that we get by taking the CFT and deforming by this coupling, and we're going to probe it at different scales. So this flow has some scale associated to it, which is determined in terms of this coupling constant. So there's some C here, and there's some, just using dimensional analysis, there's some length scale, there's some relation between the coupling and this length scale. And so this is sort of the crossover scale. So if we probe the physics at very short distance, which is much smaller than this scale, then we'll see properties of the UV CFT. At very long distances, we'll see properties of the IR CFT. And so there's some physical scale that we use to probe it, which in this case is going to be the radius of the ball. So R, the radius of the ball. So we're imagining we have a ball-shaped region. We have this theory that's undergoing this flow, and then we're probing it at different scales. Okay. So yeah. and whether we're, so whether, sorry, for example, let me just do an example. So let's just do the 2D case. This is the simplest and actually the most, then, so if we're calculating this entropy as a function of R, then if we're at very short distances, but still above the cutoff. So R is much bigger than the cutoff, but it's much smaller than this scale associated to this picture. So we're really probing UV physics, so we can just use the UV answer for the entanglement entropy of this interval now. And that's just CUV over 3 log R over epsilon. And for R much bigger than this scale, so now we're probing properties of the infrared, CFT, then we expect the entanglement entropy to be CIR over 3 log R. And now there's sort of a question what we put here. And one thing you can sort of think is that when you're very close to this infrared fixed point, then this C parameter sort of appears like a cutoff, right? If you tried to flow back up, there's going to be all these irrelevant operators that start turning on, and they will sort of set some upper bound, which is some cutoff. So it's natural to put C here. However, you also have to remember that your entanglement entropy always has a UV divergence near the boundaries, and that UV divergence is always probing the UV CFT, right? It always knows about properties of the UV CFT, so actually it always has to multiply CUV. So there's always, so even though this is the expected behavior, there's some correction, which is CUV. So like this, easier for me. CIR plus CUV over 3 log some length scale over epsilon, and then there can be some constant here. Okay, so I just put this term, it won't really play a role, but it's to get the right UV divergence, right? So the epsilon is our cutoff that we use to compute the entanglement entropy, and it's always probing the UV.
If you have like a two-step flow, that be the original CFT, you show something.
With the twist operators, did you say?
Two-step flow. Right?
Oh, the two-step flow? Like something more complicated in this picture? Yeah, it's always the top one. Yeah. In the way that I'm describing things, at least. So where I'm sort of using a physical scale to probe the flow. This is the picture. So now, okay, so all right, so what we're now going to try to do is sort of take this interval and move it, right? So we're going to try to change the scale and to see if we can get some bound on the behavior of the entropy as we do that. And so what inequalities might we use, it's sort of, well, at a first pass, this is what you might do. You might, so it's natural to try to use some entropy inequalities. So we're going to use strong subadditivity.
Associate some function with these entropies?
Sorry?
Are you going to associate some function with these entropies? Because you mentioned earlier that there is some sort of inequality in the C-theorem. I don't see a C-theorem here.
I haven't proved a C-theorem yet.
Oh. Sorry,
yeah, you're getting, yeah, so this is just the expected behavior at the fixed points. Yeah, I should have said that. So this is very, and so the question is, what's the interpolating function? Well, we actually know that there's a C-theorem thanks to Zomolodchikov in 2 dimensions. So This is 2D, so we know that this is bigger than this. However, what we want is we want to show that we can find some function that, that interpolates between the UV and the IR, which proves that, in a different way, right? So this is going to be a very different proof to the original one. Okay, so the first pass, let's consider two overlapping intervals. Let me call it beta and alpha. So these are all on the t is equal to 0 slice. And let me take the lengths to be the same. Then I'll call this length beta. I'll call this longer thing L2, and this shorter thing L1. So these are the, if you like, this is the union. So L1 is the length. L1 is the length of the union of the two intervals, and L2 is the length of the intersection of the two intervals. And we're taking the original intervals alpha and beta to be of the same length, which means that then LA has to be L1 plus L2 over 2. And so what we want to do is apply strong subadditivity in the following form. So SSA as S alpha plus S beta should be bigger than the intersection plus the union. Okay, and so plugging in, and then the other thing that we need is that in a relativistic theory, and I should have said this, we're asking about entanglement entropies of the ground state. And in a relativistic theory, all we really need here is actually translation invariant. So we need everything to be translation invariant. So these things are just functions of the length. So now I can write these entropies as just the function of the length of the intervals. And so this gives me some relation between the lengths of the intervals. So this is kind of what we want, right? And so what is this telling us? It tells us that S is a function of L. So S as a function of L S as a function of L should be a concave function. Right? This is the definition of a concave function, so it should be concave like this. Okay, but we kind of already knew this, right? So the entanglement entropy, at least in the CFT fixed point, is like C log L, and log L is a concave function like this. So at least it satisfies that. That's nice. However, this inequality doesn't actually kill this term. And this is kind of something we want it to do because we want the inequality to be saturated at the fixed point. Okay, so it's not saturated at the fixed point, and so this doesn't actually work. And this is actually kind of fortunate if you think about, well, for various reasons, we really haven't used dynamics. We haven't used the Hamiltonian. We're just probing properties of the state. And if you think about in ADS CFT, again, Matt Hedrick's discussions, all of these entropies would be computed on some fixed time slice. And that's sort of a trivial thing. In some sense, it's a trivial. It doesn't know anything about constraints on the bulk dynamics. So now I'm thinking if you tried to do this in a holographic example. This is going to be a general discussion, but if you did it in a holographic discussion, the inequality where the intervals are all on the same time slice is not sensitive to interesting physics in the bulk. In particular, it's not sensitive to the null energy condition in the bulk. And we have reasons to believe that from other ways to understand RG flow in ADS-CFT that it depends sensitively on the null energy condition in the bulk. Yes.
In the bar, in a slice, do you see the C-theorem?
Say that again?
Do you see the C-theorem, the lower thing that's in a fixed space?
No, so that's what I'm saying. So this does not give you the C-theorem.
Not with that relation, but just with other methods in the lower field, like, I don't know, the fact that
Oh, whether you see it on a fixed slice? No, so you need to know some dynamical information. I mean, you need to know you need to know the null energy condition in the bulk. So so if that's violated, then you violate the holographic C-theorems. And so so I think there's some, anyway. So what we need to do is we need to do something which involves dynamics. So we need to have the intervals not on the same slice, okay? So, did I really? Okay, so. Okay, so we're going to use, so the better approach is to well, we're going to use various things that you've learned, over the course of the week about entanglement entropy. So one thing that we've been told is that the entanglement entropy of some interval is really a function of the causal diamond, so the domain of dependence of that interval, d of A. And so, it's the entropy associated to this slice is the same as the entropy associated to this slice is the same as the entropy associated to this slice.
Maybe switch from ball shape into a slice.
Sorry, yeah, maybe I wasn't so clear. This is the two-dimensional case. In 2 dimensions, a ball is an interval. So the ball is interval. And so this is the interval, but now I'm drawing pictures in time, right? So this is in real time. These pictures are in real time. Okay, so that's one piece of information we're going to use, and the second piece of information, which is kind of obvious, but in a relativistic theory, at least if you don't go beyond the light cone, the entanglement entropy, well, it should just be a function of the length, but it should just be a function of the proper length. Okay. So there's some universal function S of sigma which depends on the proper length and allows us to calculate entanglement entropies, at least in the vacuum state, even under this RG flow for boosted intervals. Okay? Questions? Okay, so the better setup is, well, the way to describe it is to think about the light cone of a point. So we just define this light cone. And then we're going to consider a Cauchy slice made of 3 parts. So x1, x2, x3. Okay, and then we're going to apply SSA in a form where we take, at least in the form that I wrote somewhere up there, if we take alpha to be x1, x2, beta to be x2 union x3. So this and this is alpha and this is beta. Then applying that inequality, we get S of x1, x2, S of x2, x3 is bigger than x of x2, S of x1, x2, x3. Okay. So,
sorry, no, but
yeah.
alpha and beta are not disjoint, obviously. They're going to include x2.
Yes. Yeah. So, sorry. Yeah. This is alpha. and this is beta. Okay, so then, we use the first rule for these various cases. So the first rule means that if I look at, say, x1, x2, then the entanglement entropy of this funny region is the same as the entanglement entropy of this region, right? So I can deform this region in a space-like direction to this region, and so now it's just the entanglement entropy of an interval which we know the form of, right? And similarly for x2, x3, you can relate that to the entanglement entropy of this space-like interval. And x2 is already a space-like interval, but x1, x2, x3, all of them can be mapped to this space-like interval. So then we get S of, let me call this dashed line A, this one B, and this one C. Then we get S of A plus S of B is bigger than S of x2 plus S of C. And then we use Lorentz invariance to write these as just functions of their proper distance. And notice that just some basic geometry. If this is L1 and this is L2, it's not hard to show that these lengths are the same, and they're given by the square root of L1, L2. Okay, so I'll leave this as an exercise. Check that. So that, right, that's the length of these diagonals is the square root of L1, L2. So that means that these two terms, A and B, just become twice the entropy of the square root of L1, L2 is bigger than the entropy of L1, entropy of L2. Right, okay, so this is going to be the better inequality. And to analyze it, we take L1, so we're going to just take L1 and L2, which are these original lengths, to be just small deformations of each other. So we're just going to make this picture really small. These deformations are going to be really small. So L1 I'll call R, and L2 is R plus a little bit. And then you expand. And at second, so importantly, at first order, everything cancels. So you don't see anything at first order. That's actually just a consequence of strong subadditivity, of the form of strong subadditivity. However, at second order, you get something. And what is that something? You get is equal to, sorry, let me go up. Well, so if you expand at second order, then this becomes a bound at second order because the first order term vanishes and the zeroth order term. And so you get this bound plus S prime of R is less than 0. And so you can rewrite this as d by dr of R ds dr is less than 0. And so this is something as a function of radius which is decreasing. So this is what we're going to call our C function. And a nice property of this form is that at the fixed points you can plug in the form of the known entanglement entropy. It goes like a log of R. It's a log of R in both of these, but the thing multiplying is different. And so this is CUV up to a factor of 3, which I should put a factor of 3 somewhere. Let me put it here. This is CUV for R much smaller than this scale, C, and it's CIR for R much bigger than the scale. So, right, so this proves the C theorem because, this is some quantity that interpolates between CUV and CIR, and its derivative is negative. So,
Did we use somewhere that inequality that you wrote in the statement? That,
SSA?
sorry, about the C theorem that that a C function in UV and C function in IR, there is some inequality there.
That's what we're proving, yes. We're not using it, we're proving it.
But you started with that assumption, right?
No, I did not start with that assumption. I mean, it's known independently, but I'm proving it using...
Of that statement.
Yeah. Mm-hmm.
Okay.
Yes.
Is this C function the same as the one on Zalmlogikov, or is it related?
No, so it's actually explicitly different. It's a different C function. So it has a very different form. It interpolates between the two same things, but it has a very different form. It has very different properties. For various reasons, actually, it has less nice properties, I think, than the Zalmlogikov C function, but it still proves this C theorem. It's different. Yes.
Can you relate the C function to some two-point functions of the stress tensor?
No. So this is some very non-local thing, right? So it's not. So the Zalmlogikov C function is related to two-point functions of the stress tensor. However, this is a much more non-local thing. Now, the interesting thing is that it seems, standard methods, even in 4 dimensions, Kolmogorski, Schwimmer proved the A theorem using more standard methods related to local correlation functions. However, in 3 dimensions, the only way to prove the F theorem is using these kinds of techniques, and it is related to this non-local quantity. So good. So just to summarize, there was so there's some function as a function of R, C of R. You can prove it starts at CUV, it has some form, but it's a monotonically decreasing function and ends at CIR. That means that CUV is bigger than CIR. And so this is really beautiful. It's very simple. It's not a complicated argument at all. It's sort of physical. Actually, you might try to understand what it means, right? So you have entropies and they're changing on different length scales. So there should be some meaning to this. I don't think it's fully been worked out, but there should be some meaning. And then the natural thing is to try this in higher dimensions. And Cassini and Horta did this in 3 dimensions, and I'm not going to have time at all. It's much more complicated. So this is beautiful. The 3-dimensional version is much more complicated. You have various issues trying to generalize this to higher dimensions. And I'll, as my last word, I'll leave an exercise for you, which is to find a better way than that. There should be a better way, but I don't know what it is. Okay, let me finish there.